In this video, we will discuss the initial value problems, the Picard-Lindelöf-Cauchy-Lipschitz theorem, and flows. Before we start talking about any theorem, let's actually go back to a few definitions. During the introduction, we explained what an ordinary differential equation was. It is an equation that relates a function with its derivatives with respect to one variable. And as we know, if you look at y prime equals my for any m in R, then, well, actually we know the solution. The solutions are y of x equals lambda exponential mx for any lambda in R. In other words, you have an infinite number of solutions. You don't have one solution, you have an infinite number of solutions. But if you specify y of 0 or y of anything at that point, then lambda will be provided as a unique function of y naught. In other words, you have only one solution to that problem. Well, this leads to the definition of an initial value problem, IVP in short, or Cauchy problem, which is an ordinary differential equation and a specification of the value of y at a given point, which will be called an initial condition. So an IVP is an ODE plus an initial condition. And you can see why this is interesting in terms of modeling. I mean, if you think about it, the initial condition will describe the system at a given time, and the ordinary differential equation will describe how it evolves over time based on some kind of a model. So an IVP will describe the state of a system at a given time in the future. That is why it is interesting. Now, before we move on to the theorem, I would like to also give the definition, which you might already know, about the order of an ODE. The order of the ODE is determined by the term of the highest derivatives. For example, y prime equals my is a first order ODE, and y second plus 2y prime is equal 3, and plus 3 equals 0 is a second order ODE. In an ordinary differential equation, the derivative is with respect to one variable only. In the examples from the previous video, the variable was t, which modeled time. That's often the case. It's not always the case, but it's often the case. Now, when we have only one variable, it's called ordinary differential equations. But when we will have several variables, and that will be the case very soon, it will be called partial differential equations. And obviously, this class is about PDEs, partial differential equations. So starting at the next chapter, we'll start having more than one variable with respect to which we will differentiate. But this chapter here is actually here for two reasons. Number one, because, well, first, let's start with simple things. And second, we will use the material of this chapter when we will talk about parabolic equations in the very last part of this class. So it's important we understand, or we basically recall, what is an ODE and a few things about ODEs. In terms of notations, this equation is often denoted y or u. The variables often denoted x or t. This is not a rule, but that's kind of a custom. And the ODE, y prime plus 3y of t plus t squared, can be denoted with d over dt. That's another possible notation, or with a dot to say it's the time derivative. And often, or sometimes, we will actually drop the t and just say, okay, it's y prime equals 3y plus t squared. Let us give a few formal definitions here. So let's t naught be in R, or t0 if you prefer, that it will be given. Let's I be an open interval containing t naught. Let's U be an open set of Rd. D is the dimension of the space. So if y takes its values in R, d is equal to 1. If y takes its values in R2, then d is equal to 2. F is a function that goes from I times u to Rd, and y naught is an element of u. And we will write our initial value problem as this. Basically, y of t naught equals y naught. That is the initial condition. And f, the function f, will basically be the one that will describe the ordinary differential equation. And it will describe it in a sense which is y prime equals f of t, y of t. Let me give you an example. If you look at the ODE, y prime equals 3y plus t squared, and the initial condition y of 0 equal 1, then the formal definition here will be such that we have t naught equals 0, y naught equal 1, that is y of 0 equal 1. I is an interval that must contain t naught, and we will say, well, r is perfectly adequate, so we'll choose r. We could choose something smaller, but we do choose r. The dimension will be 1 because y takes its values in r. And u, again, can be something smaller. It needs to contain 1 because that's y naught, but we can actually take the entire real line. That works as well. So here is an example with the formal definition. And the main question at this point is, what is the function f that will turn that y prime equals f of ty into that ODE? Well, what you can do is, or what you have to do, is to choose f of tx equals 3x plus t squared. Now, if this is not clear to you why that is the f we need to choose, then I suggest you stop the video and you understand how this works, and then you reconvene with us. Let me give you another example. Let's choose the pendulum equation that we described in the earlier video. We had theta second plus g over L sine theta equals 0, and that was the ODE. And the initial condition will be the position of that pendulum when I start, and that will be basically theta of 0 equals pi over 2. In other words, I have a 90-degree angle when I start the experiment. And the speed of that pendulum at that point is 0. So I give the position and the speed, that is theta of 0 and theta prime of 0. Now, I'm a little confused here because if you look at what we have y prime equals f of t, y of t, which seems to be first order, and I'm trying to fit in something which is second order. So how can I do this? Well, I can do this by using a function u that will be the vector theta of t, theta prime of t, and that will be my vector u of t. So that vector u, if I choose this vector u, then I can write my second order equation into a first order equation. And here's the way I do it. I'll do f of t x1 x2 equals x2 for the first component and minus g over L sine x1 for the second component. And if I do this, then basically I can reduce my second order ODE into a first order ODE. I just have to increase the dimension of the problem from 1 to 2. And this is why I choose d equal 2. Now, if this is not clear to you, again, please stop the video, make sure you understand completely how this works, and then come back with us once you have fully understood how this works. Now, let me give you the definition of the slope field associated to an ordinary differential equation. That slope field will be for each t and x, I will associate the vector 1 f of tx. And often I will normalize it just so it's easier to see on the graph. For instance, let me give you the slope field associated to the ordinary differential equation y prime equals 3y of t plus t squared. We just gave function t a few minutes ago, and here is the slope field associated to it, which means that for any tx, I will actually draw the vector 1 ftx, which I will normalize so it's easier to see. And I can define the integral curve of the slope field, which is basically for any y of t naught equals y naught, then I can actually put the point on the slope field and draw the solution, and that will be called the orbit. Here's what I do for y of 0 equals 0. The solution is actually here in red. And if instead of doing y of 0 equals 0, I do y of 2 equal 2, y of 0 equal 2, then I have another solution, which is now in green. And of course, the vectors to the slope field are tangent to these orbits, to these integral curves. Now, there is a natural question that arises, which is, do we have solutions to ODEs? If you basically encounter an ODE, can you be sure that there will be a solution? Can you be sure that there will be only one solution if there is one? That is a very interesting question, of course. And to answer this question, or actually to give a sufficient condition to have existence and uniqueness, we have the local Picard-Lindelöf-Cauchy-Lipschitz theorem, which is actually called Cauchy-Lipschitz in France and Picard-Lindelöf in most of the Anglophone countries. So since it's a class given in France, but in English, we'll call it the Picard-Lindelöf-Cauchy-Lipschitz theorem. Now, what the theorem states is that if I have an IVP and I have two properties, which is continuity with respect to the first variable and C1 with respect to the second variable, then there exists an epsilon, a positive epsilon, such that the initial value problem will have a solution on T0 minus epsilon and T0 plus epsilon. On that interval, there will be a solution. And on top of this, it will be a unique solution. This is what the theorem states. Now, how do we prove this theorem? Well, we're going to give a sketch of the proof. It relies on building a sequence that will have a fixed point. And that sequence is given by phi 0 of t is y0. That is a constant function. That's the first iterate of our sequence. And for every k, I build phi k plus 1 as a function of basically y0 plus the integral between t0 and t of f s phi of k of s ds. This is known as Picard iterations. And before you took this PDE class, there was a requirement, which is the CIP class, the Convergence, Integration, and Probability class. And during that class, you actually proved that the iterations had a fixed point. Now, I would like to show you something. If you look at this equation, y of t equals y0 plus integral between t0 and t of fs ys ds, or if you look at the IVP, well, then basically they are equivalent. Now, it means that if you have a fixed point to the Picard iteration, then you have a solution to the IVP. And again, during the CIP class, you proved that you had a fixed point. So that fixed point, let's call this U, will be the unique solution to the IVP in the neighborhood of T0. Well, that proves the existence. Now let us prove uniqueness. To prove uniqueness, we will take two solutions to the IVP, U and V, and we will prove that U is equal to V. And actually, it's easy to prove once we have what we call the Gronwall's inequality. The Gronwall's inequality states that if t is a positive number and if phi and psi are continuous functions from 0t to r plus, and if on top of this phi of t is smaller than a non-negative constant a plus the integral of between 0 and t of phi psi, then I can bound above phi by a times exponential integral between 0 and t of psi of s ds. So from the Gronwall's inequality, we actually prove that U is equal to V. Therefore, there is uniqueness, and subsequently, the theorem is proven. Now, that theorem was stating a very local result around T0. We can be interested in having a solution on the more global scale, and that is what the global Picard-Lindelöf-Cauchy-Lipschitz theorem is about. The hypotheses are of these ones. First hypothesis, we need to have a continuity of the function. And again, it's continuity with respect to the first variable, which means that t gives f of tx. Here, x is a parameter, and we have a function of the one variable t. Okay, t gives f of tx. Second hypothesis, we want to have a globally Lipschitz continuity with respect to the second variable, and then this time t is the parameter, t is fixed. And what it means is that and what we want is that this global Lipschitz continuity is with a Lipschitz constant that is independent of the parameter t. What it means is that there exists an L which is independent of everybody, positive L, such that no matter what t I choose, and no matter what x1 and x2 I choose, then the norm of ftx1 minus ftx2 will be smaller than L times the norm of x1 minus x2. And if this is the case, if both criteria are met, then the initial value problem has a unique solution on I. Now, let's define well-posedness. Well-posedness of an ordinary differential equation, and later a partial differential equation, is what happens if we have three properties. The first one is the solution exists. The second one is the solution is unique. And the third one is that the behavior changes continuously with respect to the initial condition. In other words, if instead of having y of t naught equals y naught, I have y of t naught equals y naught plus something small, then the solution will be close to the solution I had with y naught. So if I have a small perturbation of my initial condition, the solution will be close to the solution that I would have without the perturbation. And you can see why this is important from an engineering point of view, is because you never really have the exact measurement, or you never really have the exact possibility to set a value. So it is important that the small perturbation will not completely destroy your model, or will destroy your system. It's really important. That's why well-posedness in the sense of Hadamard is so important. And if it's not the case, then we say that the ODE is ill-posed. Now, the Picard-Lindelöf-Cauchy-Lipschitz theorem gives an answer to the existence and the uniqueness. But as you can see, it does not give you an answer to the third question, which is the continuity of the solution with respect to the initial conditions. Now, a corollary to what we just did is that if k is an integer greater than 1, and if f is in ck, then the solution to the initial value problem, which is here, will be in ck. Now, let me interpret geometrically the Picard-Lindelöf-Cauchy-Lipschitz theorem. The first thing it says is that there is existence of the solution. In other words, there is an orbit. The second thing it says is that two orbits coming from two different initial conditions can never intersect. If they were to intersect, it would mean that we don't have uniqueness. Now, let me state the theorem. Let f be a function that is c2 on I times u. Let t naught be in I. Let y naught be in u. Then there exists a neighborhood of t naught y naught that I will call j times v, and a function phi, or phi t naught, that is a function which is c1 from j times v, my neighborhood of t naught y naught, to u. And that function phi t naught will satisfy the initial value problem. In other words, it will satisfy these equations here. Now, to help us understand this equation better and what this function phi is all about, phi t naught is all about, there's my daughter Charlotte, who is here with us. You can get on your stool, Charlotte. Hi.
Hi, my name is Charlotte, and I'm 6 years old. I have a little game that I played when I was little. It's called the Leaf on the Water. I took a leaf, put it in the water, the leaf floated. I thought the same, but actually it floated.
And what we can see here is that when we put the leaf, when Charlotte puts the leaf on the stream of water, basically this leaf goes down the stream. And just think of phi t naught as the function that will tell you where is the leaf, provided you know what is the time t and what is the position x where Charlotte put the leaf to begin with. So let me just clarify, and just to simplify things, let's assume that t naught is equal to 0. That is the time when Charlotte puts the leaf on the water, right? Now, x is the position where she puts the leaf, and you are interested to know what is the position of that leaf t seconds after Charlotte put the leaf on the water. Well, that is exactly going to be given to, this is going to be given to you by phi tx. So again, phi naught, phi 0, phi t naught. Phi will take two arguments, the time t, the position where Charlotte put the leaf to begin with, and will tell you where is the leaf. That function, phi t naught, is called the local flow to the ordinary differential equation at t0.